Yeah, thank you very much. So I'm going to preface this talk by saying I'm going to say some spicy things to start this. Stick with me to the end. I think that I just couldn't find an easier way to just kind of motivate exactly what's going on here. So this is going to be a talk that's like, semi about the technicals, but also a lot about like the theory and the philosophy of designing package ecosystems. And so yeah. So I want to start there. I want to start on the philosophy and of an optimal control ecosystem, right? Because there is optimal control today, right? We're there is. It's not like there's nothing there, right? So if I was to go to the jump documentation, even all the way back in like 2014, right, you'll find that there's like the same example, nonlinear optimal control of a rocket, right? And what you do is if you want to do nonlinear optimal control inside of Julia or Python with Pyomo or like all of these different interfaces, what you can do is you can just define an optimization problem where you just say, okay, I want to optimize the system that has an ODE. Let me just write out the ODE as the derivative is, x of the future minus x of the past divided by delta t, okay, I can do this. I write this into my optimization library and then I solve this and boom, I get an optimal control solution, right? Aren't we done, right? But I think that there's just a lot of issues with this approach, and I think that this is acknowledged in this ecosystem, right? The user has to choose a correct collocation. What I just told you with Euler's method, it's like, oh, well, that's unstable, so maybe use implicit Euler, but but then use these Lobato or these Rodau collocations, right? There's all this kind of math in there that's not abstracted from the user, right? They have to write a lot of really deep code in order to do this inside the optimization system. They also have to choose a correct DT, right? Because then they have to say, okay, I want to write out my system where I have the derivative at every time point. Well, I'm going to choose dt to do this, right? If you look at all these documentations, these examples, they're all fixed time step, which we know is going to be inexact because the behavior of solving real nonlinear systems. It's also missing any connection to any other modeling tool, right? We've heard a lot of things around ModelingToolkit in like biological cases, right? So a biologist wants to come in with an SBML file that has 1,000 differential equations inside of it that have been verified to be a heart model, or people want to come in from Modelica and be able to bring in their 10,000 equation model that's describing a vehicle. And so then you say, yeah, just write the jump code for that. That's not that easy, right? It's like there's thousands and thousands of equations in these other spaces, and now we've kind of thrown out all that information when we get to this optimal control space. And it also just doesn't give a very fast process. And I'm going to explain exactly why later. But it's like this is a general approach to solving the problem, but general approaches generally don't end up being as efficient as something that's very highly tuned to a given type of a problem, right? And so this is something that you can do today, right? I'm not saying that you can't solve optimal control, but I think that it's not the kind of interface and the kind of way we want to be doing this in the future. But then you go, okay, there's actually all these other libraries in optimal control. In fact, there's a talk earlier in the other room that that was going on, right? There's infinop.jl. Pyomo has a DAE part. There's Ideas, which is also built on Pyomo. There's Casati in the Python space. There's gpops inside of the MATLAB space. There's OpenMDAO, right? And what all these kind of do is they let you write down instead of actually just directly writing the nonlinear optimization problem. You instead write it one level above, where you give the system the differential equations, right? You say, hey, look, I have these variables like x of t, and I have a differential equation, and now I tell you, do orthogonal collocation, do Lagrange-Rodau, discretization, and it will do exactly that step that I talked about before, right? Where it will generate a large optimization system to solve, right? But I think that there's still many problems, right? Like all the problems that I mentioned before are actually still here, right? The user has to choose a collocation method that is appropriate for the type of equation that they're working on. They have to choose a DT because a lot of these are still, in fact, all the ones I mentioned, I think, are still fixed time step, right? And there's no connection, again, to any of the Modelica or the SBML. All these issues still exist within these libraries. And so I think that, even though there is an optimal control ecosystem that's been built up, I think the problem is it's missing this design element that's connecting it to the rest of the world, right? It's treating optimal control as like this isolated problem where you go and write your equations for that, and that's the only thing you do there. You don't do anything else in your entire life. You just only do optimal control, and this is the only library you need, right? And I think that philosophy is kind of just not right. And so, again, I told you this is going to start spicy. And so I think the problem with optimal control today, I don't think it's the work that people have done, right? I think that people have built some great libraries. But I think that the designs just weren't correct from the start to solve the large-scale types of problems that we want to solve with the Julia ecosystem, right? And so what is my fantasy optimal control library supposed to look like? Tons of text, right? But here, it's rather simple, right? It should be easy to use, right? Like if an optimal control library can't solve my problem, then it's useless, right? So it needs to be very easy to write down high-level equations, but also import, equations from these other sources like SciML. You want to be able to bring in data from chemical property libraries, and say, hey, I have these chemical properties that describe the latest refrigerant properties. Now do optimal control in an HVAC system, right? Like you want to have all that be automatic. You want things like Modelica, Simulink, AimSim to be able to pull in. All these industrial models that people are using to build cars. I want to do optimal control on a real car, not like 5 ODEs that I can easily write down, right? And so and it needs to connect to this wider world. And when you do that, you need to also make it so that way it doesn't just ignore the other analyses, right? Because you don't just do optimal control. After you find the optimal controller, you want to say, hey, now let's build an embedded, let's build a bifurcation diagram and see where this optimal control makes sense, where does it no longer make sense in parameter space, and now let's generate code so that goes on the car, right? This whole other set of things that you do with the model, you want to be able to do that on the same model specification, and you also want to do things like integrate machine learning, like all the things that we hear about in all these other talks, right? Want to be able to take a model, integrate the machine learning, and then do optimal control on the model that I've now improved, right? So that's what I mean by easy to use. It's probably not the same definition of easy to use that people had in the past, but this is what I want as easy to use, right? That every model that everyone's built before, I can run the system on it. And then I want to be able to take that and I want it to be fast, right? Because if it's slow, it's useless, right? And so it should be scalable. It should use sparse reverse mode AD, fast NLP methods, GPU parallelism, and everything around, right? And the other key things is that it should be able to just figure out, like, hey, if my problem is actually not nonlinear, if it's quadratic, just use a quadratic thing. If it's convex, just automatically do this, right? I mean, these are things that you could do in the library. If you wrote down the optimization problem yourself, you can recognize it and say, oh, this is what I need to do. But the high-level system should do that, right? If we're dreaming up this system, and it should automatically simplify models, right? If you write down a bigger set of ODEs, it should be able to say, hey, I could solve this smaller set. It should use analytical properties and do anything that you can do yourself as an idea. A symbolic system should be able to do it for you. If the algorithm's in your head to be able to simplify things, and you go, oh, I always change it from here to here to make it easier to solve, then that should be able to be built into the computer itself, right? And it should be robust, right? It should have the all the stable collocations, Lobato, Radow methods, but it should also be robust in the sense of it should change DT for you, right? You start with a grid and should be able to adapt the grid automatically, so that way it gives you something that is numerically stable and robust and giving you the right solution every time. And then it should be easy to contribute to and develop, right? Because if there's very few people working on it, then it's never going to be able to get done. And so it needs to have a separation of concerns between what's working on the solver versus the modeling interface and all these different aspects. And it should connect to different problems beyond just optimal control. So that way you have people who are working on biology and people who are working on physics and people who are working in industrial modeling spaces contributing to this whole core, even if they don't even care about optimal control, right? You should be able to get all of their improvements. So that's why do I want an optimal control library. And when I say it like that, then you can say, yeah, okay, these don't satisfy that, right? Of course they don't. But the real question is it possible to be able to design a system or an ecosystem for optimal control like this, right? And so for a very long time, now I guess about a decade, in SciML, we've always said, oh, we don't have an optimal control tool, right? And I'll show you exactly why, but what we've built towards. So SciML's approach to optimal controls is simultaneously address all these points by making sure we design in a specifically different way than like what I'd call like the Python brain or the MATLAB brain, monolithic ecosystem style. What we're doing is we're implementing optimal control as a general dynamic optimization interface on ModelingToolkit. And this means that everything that comes with ModelingToolkit then always extends to the optimal control universe. And then we're separating out the solver development and actually using the tools that are being built for boundary value problem solvers as a way to kind of jumpstart these more advanced solver pieces. So I'm going to tell you about these two pieces in more exquisite detail. I'm going to start with the optimized solvers because it turns out that story is actually easier to talk about, right? So how do you build a boundary value problem solver? Well, the way that you build a boundary value problem solver is you do orthogonal collocation methods like Lobato methods and Radow methods, where you write out the differential algebraic equations and you solve this collocation over space and time, by writing out a large system of nonlinear equations that you then solve for the zero. It should sound very similar to what I just described at the beginning with the nonlinear, optimization, because it is extremely similar. The internals of a BVP solver are almost exactly the same thing. But the key here is that a lot of what we've done in boundary value diffie-q is optimizing this kind of solver process specifically to the types of equations and the types of nonlinear systems you get out of this process. This was an entirely different talk that I gave at JuliaCon 2025. So you want to know all about half hour of just the details of the BVP solver, go check that out. I'm just going to highlight two things here. One thing is that it uses a specific mixed mode automatic differentiation because the collocation part actually differentiates optimally with a form of blocked forward mode automatic differentiation, whereas then the part that you have with the boundary conditions ends up being optimal if you do sparse reverse mode automatic differentiation. And so it asynchronously does both forward and reverse mode automatic differentiation at the same time with sparsity handling in there as well, with the automated sparsity detection. And we do that to be able to generate this kind of matrix that has this arrow structure. And then we have our own specialized BLAS that we built called almost banded matrices.jl that is faster than using sparse matrix solvers for specifically these kinds of matrices, right? So this is what I mean by, like a general NLP solver is not fast, because if you just throw a sparse matrix solver and you just throw automatic differentiation on here, you won't get this mixture of forward and sparse reverse mode plus a specialized BLAS for this exact type of problem, right? And so this is what so we spend a lot of time in the differential equation solver library. So this is what people like us for. We're kind of these nerds that sit there and just continue to optimize these solvers for God knows what reason until we end up with these things, right? But not only that, not only do you get solvers that performance, but also with this boundary value problem solver, there's a differential equation under the hood, and so we have ways to be able to do adaptivity, right? Because a core of the SciML ecosystem is to not just give you a solution, but also be able to give you a solution to tolerance. And so there's a whole adaptivity algorithm that's using the interpolations between different orders, yada 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 yada. I'm skipping over this again. That's in the boundary value problem talk, but it uses this to be able to automatically adapt DT, so that way you can start with very large time steps and split the intervals and end up with non-uniform grids automatically generated based off of putting more grid points where the problem is harder and less grid points where the problem is easier, right? So it's a performance thing, but also a correctness measure. Now, this is all about boundary value problems, and you're like, okay, well, I thought this was about optimal control, right? Well, what are we doing here? Well, again, these are collocation methods, right? They were doing Lobato and Radow collocation, so it's almost the same thing, except a boundary value problem solve has conditions at the beginning and the end. Well, not quite. I mean, you can generalize the idea. So what we did with boundary value diffie-q is we said, well, you can have boundary conditions at the beginning and the end, but you can also have the boundary conditions right in the middle. Why not, right? That's a multi-point boundary value problem at that. But what you can also do is you can then say, well, I can, if I have boundary conditions, I can also just add other equality conditions to it, right? Maybe you have to solve, maybe the solve is slightly different, but I can just add any other equality conditions I want. And if I can also add as many equality conditions as I want, I just need to be able to change the solver to be able to handle any equality conditions. And if I have all these, maybe then at the same time, I could just minimize a cost function. And oh crap, all right. So now the boundary value problem solver is actually a dynamic optimization solver. And so it gradually morphed. I mean, again, all these same pieces, the adaptivity in time and the collocation methods and the specialized automatic differentiation, that is all there, but by just adding a few extra pieces to the BVP solver, we get something that's actually a tool for dynamic optimization problems. And so what we're going to be doing here is we're going to be splitting the documentation, so that way we keep a complete documentation for boundary value problems, specifically for people interested in that, but then also giving a different set of documentation that shows how to use the same solver for optimal control problems if you want to be able to directly write to it, right? And so this then gives us a solver. This is then the optimized solver that we're talking about, something that's able to use GPUs and able to do this mixed mode automatic differentiation, all and be adaptive in time with the automatic time grid adaptivity, all of these things automatically as part of the system, right? So that this of course, once you hear that, you're like, okay, I could see why that's going to do better than just writing out the nonlinear system into something like jump. Like jump is really good, but it's not specializing on the problem like that, right? But then the other thing is, what about that symbolic interface? Because not a lot of people are going to want to directly write the code to the solvers. You want to just write down, very high level equations and get something out. And so this is what it actually looks like. So actually this piece is I want to mention here that this optimal control interface, it's missing the last PR merge as of 2 weeks ago. Like we're still trying to get a few things here, but this last piece for the optimal control is merging within the next 2 weeks or so, right? So then the ModelingToolkit interface, like the symbolic interface, is actually already in ModelingToolkit. And if you've seen ModelingToolkit before, right, you've probably seen things that look like, okay, I give it, I have variables, I have parameters, and I have my system. My system takes in these differential equations. It's actually exactly the same as every ModelingToolkit model, but now all I'm doing is I'm saying, hey, instead of just having differential equations, I'm going to add a cost function and constraints to it. Those constraints can be equality constraints and nonlinear and inequality constraints, right? So the same exact ODE code that you have, if you just add constraints to it, boom, you're now in the space of dynamic optimization, right? We then have to be able to check things, so that way we say, oh, you can't generate just to an IVP ODE solver because it can't guarantee the constraints are there, but the exact same underlying symbolic code works as the definition for the space, where you now just add new information on it. You just add constraints, you add a cost function, and now we just have to solve the dynamical system with respect to that cost function. And then inside of this space, we can then just say, hey, look, let's separate concerns here. Let's separate the concerns of what the solver is from the symbolic ecosystem by just making sure we support the different solver backends. That is something we do in modeling in SciML a lot. So for example, we have infinite op dynamic problem, jump dynamic problem, Casati dynamic problem, and Pyomo dynamic problem, right? So what this means is it takes the same symbolic definition and it generates either the jump code, the Pyomo code, the Casati code, the infinite op code, and so it's able to then use any of these tools for optimal control solving, and it'll very soon then be able to also target our new boundary value problem solvers as well, right? So again, this is now something where we're saying, hey, look, this is kind of like what infinite opt has, but now it has any ODE system that you can generate from ModelingToolkit. It's able to take in all those definitions, and it'll still code gen. You can still code gen to the same solvers if you want to be able to check the performance there. But now what we can do is we can then just say, okay, you can have any ODE that you want, but you can also add any integral cost function. I mean, again, the standard features of what you'd expect in a optimal control library then show up as these features within, now just add again, you just add a keyword argument to the system construction that you would have done in ModelingToolkit before, but now you can add an integral for the cost function or whatnot. And again, this integral isn't anything, is special or new. I mean, it's just the symbolic set integral. We just know how to interpret it as a cost, right? And so details that I've somewhat mentioned, right? I want to make sure I have time for the, but for the main part, which is like this part right here, where you say, okay, but isn't that symbolic interface just like infinite opt? isn't just like what, the @def macro of optimal control.jl, et cetera, why should I care? Why should I care that it was built in this way rather than the other macro way that showed up, right? And I think that the easiest way to show you is just to tell you about a few user workflow stories that happen because of how we've done the ecosystem integration, right? This is something that is solving the problem of ecosystem integration and composable software development. And I want to show you what it then looks like, what is enabled now that we've done it through this way, right? And so here, for example, right, we have Dyad, which is a system for building models in a graphical way. There are entire groups of individuals that are building these models. There are these entire groups of people that are building these models, where you have these pre-built models of motors, of cars, and all these aspects, right? And it gives you, these highly detailed hundreds of thousands of equations for HVAC systems, for cars, for lithium-ion batteries. And you can do things like import FMUs from other ecosystems, AIMSIM, Simulink, Modelica, and you can build up these really highly detailed dynamical systems in ModelingToolkit. And because Dyad lowers the ModelingToolkit, this is now one of the systems that you can do dynamic optimal control on, right? There's nothing you have to do to bridge over to using these tools. These hundreds of thousands of equations suddenly, boom, all the solvers, infinite opt, jump, and all these things, even Pyomo and Casati, work on the system that we've now generated here, right? We've now built that bridge, that interface to the rest of the world. Everything that I mentioned in my previous sponsor talk, right? How we have these specialized agents for, generating physical systems and bringing in agents for translation from other languages like Modelica and Simulink, right? All of those pieces that are working with this industrial tooling now is able to target dynamical optimization libraries. So industrial users can get their entire solver, their entire models, these that they've built up over decades, and bring these into our new optimized solvers, right? And this isn't just industrial spaces, but also like biological and pharmacology fields, right? Because in the fields of biology and pharmacology, we built up this whole ecosystem where people can import SPML, CellML, BioNetGen, and all these different formats using, SPML Toolkit, SPML Importer, that have these, entire heart models that took up, terabytes of data and thousands of different equations. You can read those in and you get ModelingToolkit. But again, because of what I mentioned a few slides ago, all you do is you take your ModelingToolkit model and you put a cost model, you put a cost and constraints on it, and suddenly now you can do the optimal control problem on this dynamical definition, right? So suddenly this entire set of users that kind of saw optimal control as like, oh, I don't really know how to use that, that's kind of its own field, suddenly now it's right next to them. It's just like, hey, just add 2 lines of code and you get to use this new and cool thing. And so I anticipate that what will happen is that in some of the pharmacometrics conferences, you'll have people starting to do these things of like, oh, I am the first one to do optimal control for solving this QSP problem. And it takes them like literally 5 lines of code added to what they've done before. And like suddenly they're the new innovators in their field because we brought, because of by software design, we have brought this technique to their field, right? Rather than requiring them to come to us. And so I want to kind of show you one of the really special things that begins to happen with this, right? So here's Catalyst, which is this chemical reaction system modeling tool, right? It's able to build these high-level dynamical systems that give you these stochastic models. And okay, these stochastic models, there's nowhere going to do dynamic optimal control over things that are, we have 100 of this cell and then it goes to 101, right? These are discrete agent-based models, right? But what we do is we have an entire set of tooling in ModelingToolkit that can take these kind of discrete agent-based models and automatically generate ODEs that represent the flow of the mean, the variance, and all these things over time, right? They're called a moment closure. And on the moment closure, you get a ModelingToolkit model. And so you can take these agent-based type models, generate the differential equation model, just stick a cost function and a constraint function on there, and now you can do dynamic optimal control over the stochastic model because of how everything is composing, right? This is a story not of technical things, but of actually just making sure to build a composable modeling ecosystem. And then what happens too is that when you begin to have it in this form, you get to be able to flip to other tools, right? So you can say, hey, look, I have my model in Modeling Toolkit. I want to do optimal control with it. I want to then build a bifurcation diagram. I want to generate an FMU to be able to put into real-time controller on a real car. And I want to then be able to generate animations on the multi-body system. And one form for writing down the symbolic differential equation gives you all of these features all at once. Right. And this is because, Modeling Toolkit is something that is built together with the rest of the symbolic ecosystem, right? It's not just a, something that is just for this one set of solvers, but it's a underlying tool that was made to integrate with all sorts of ecosystems. And we're dragging optimal control into this space to say, now let's use, let's not build our own macro. Let's not build our own parsers. Let's integrate symbolics.jl on there. So that way everything that everyone else has already worked on in this space now applies to this field. And I think that one of the really cool things that ends up with this too is that it gives you an open research battleground, right? Because there's so much that you can do in the space of optimal control libraries. I look at that space myself and I just see, hey, look, you have constraints. What about using an SMT solver, right? These automatic theorem provers. If you have constraints, you can use a theorem prover to even prove, hey, look, is this optimal control problem solvable or not before you solve it? You can use things like Roeder basis tools or symbolic integration tools, right? Things that can solve problems analytically to partially analytically solve the problem before you end up generating code, right? These are things we already do in Modeling Toolkit, and now all of these things then apply to the space of dynamic optimization, just because, instead of building a new language on which we're modeling the system, we have the Modeling Toolkit system built on symbolics, and symbolics already has all of these features, right? Again, it's a story of composition. And so I gave a talk recently, actually at the last JuliaCon, fast stiff ODE-DAE solvers by symbolic numeric compiler tricks. I welcome you to check it out for all of the different, basically it discusses all the different ways in which we take a numerical problem and turn it into much easier numerical problems by using symbolic tricks, and then we solve that. Again, because of how we're now built this interface, all of this then just applies to this space as well, and we get extra optimizations on here. And so I want to end with this little kind of piece here, where in the Modeling Toolkit space, we talk all about these. You have these high index DAEs, and you do transformations of them. Like you have to differentiate the last equation twice in order to get a version of the Cartesian pendulum that is solvable. But it turns out that actually these collocation methods, they're actually solvers that directly work on high index DAEs. And so by integrating collocation methods with Modeling Toolkit, you actually get some new solvers that are actually more stable for multi-body type problems. Now, they're a bit slower, but it gives you a different set of tools. So the optimal control space is also filtering back to give you some tooling that is better for people who do non-dynamic optimization problems. I think that that's like just an interesting point to mention, that there's this like two-way flow of, if once you're building on the same space, you're getting the research flowing in both directions. And so I want to just connect back to the community to end this, because again, very, very, very clearly, it's not unbeknownst to me. This is a contentious topic because we're stepping on a lot of toes here, right? We're pointing out libraries, not just in MATLAB and Python, but also libraries here in Julia of people who are sitting in the audience right now and saying, hey, this part of library is not really needed because here's something that everyone will use instead, right? And so, of course, that is spicy. But I think instead, the real call here is to really try to find out, how do we work together, right? Because here's my point. Here's my real point here, right? Modeling Toolkit's centrality in Julia means it's going to be used for building a lot of differential equations, because it's used not just for, these optimal control problems, but it's also used for, initial value problems. It's used for DAEs. It's used by the biological Modeling Toolkit. It's used by the industrial tools, right? There's this centrality around this system already. And so, I think it's going to be the default system in optimal control, just because of how it connects together with everything, right? But even if that's the case, we can still collaborate. And in fact, I think that even gives us even more collaborations, right? Because it means that, while every new optimal control solver in C++ and every new optimal control solver ends up in Python is also building a symbolic language and then building the solver, we could just skip that step. We could just say, hey, look, there is a common solver specification, right, for how do we write down the symbolic things, and we could just all build out different pieces of the solvers, right, and in many different ways, right? So again, the people who build optimization tooling, Jump and MatNLP and all these other things, we already use all their stuff via optimization.jl and optimization.my. So whether they even know it or not, they are already contributing and collaborating with this ecosystem. So people building optimization tools are part of the system, but also people who are building optimal control solvers, we can integrate with these as backends, right? So all the things going on with optimal control.jl and all the things going on with infiniteop.jl, these can be solver backends. And what I think that this really means, though, is that each of these pieces can start to specialize, right? The SciML, we plan to be taking this BVP solver and really specializing it on the general nonlinear case, but there's so much space for people to optimize the solvers that are specific for quadratic problems, for convex problems, and so many space of methods. Also methods which automatically compile to embedded targets, models that use more forms of parallelism, right? Basically, if you have other ideas for these solvers, please go ahead and build it. We're not trying to push you out of the ecosystem. In fact, what we want to do is we want to be able to integrate it as a backend. And if you're faster, we'll tell people to use that, right? We have one solver, but we benchmark things and we just tell people to use the fastest one. So I think with this centrality of the ecosystem, we can end up making it so that way there's less redundant work, and we can start to make it so that way more people can filter in the space more easily. And then people who are interested in industrial modeling interfaces, all you have to do is continue to target ModelingToolkit, and suddenly optimal control and dynamic optimization is a feature that you get just by this interface being there. So again, I think it's like this, this Julia mentality of like, let's not build a mono package to rule them all. That you always get too few developers, right? But with a system where you have, symbolics.jl as a symbolic system, you have modelingtoolkit.jl built on top of that for models. You have boundary value problem solvers. You have optimal, Jump. You have this whole ecosystem, which it comes out to being 400 dependencies. Everyone involved in that ecosystem is here, right? And so you can make your mark by putting your own specialization in here, And I think with this, the 5 people building out IDEAS in Python, they have 3 orders of magnitude less developers than what we end up having, because it's just how we're building this ecosystem. And so I think, what we can do is we can build this all in tandem just by making sure to, not rebuild languages, not rebuild all these symbolic tools, but to build it in this style that integrates everything. So again, I think that there's a lot of spice there, but hopefully, that brings it all together in the end, because I think the goal here is to make it so that way everyone working on optimal control can finally work together, right? And so, yeah, it's again, not very technical talk. Well, it did have some things, not very technical, but it's about building package ecosystems together. And I think that what we can do in Julia will look substantially different than the other package ecosystems. And because of that, we'll be miles and miles ahead. Thank you very much.
Thank you very much. Thank you so much. I know it's time for the coffee break, but before, do you have any questions for Chris?
So thanks, Chris. I'm still chewing on your high energy, high speed presentation. But when you say, hey, the invite is there to build an integrated ecosystem, then always the challenge is, what are the interfaces or the interactions you sort of agree upon? And I guess that's where the other part of the challenge resides, right? Yeah. I cannot judge that, but how do you view that?
Yeah, I mean, that is always the problem. How do you decide on an interface? And I kind of think that what has worked, I mean, maybe this is maybe this is a bit of a statement here, but I kind of think that the thing that has worked out in the end a lot of time in open source has been, build upon the things that are working, right? I think ModelingToolkit has this system, this definition system that is already kind of in so many other domains that it's let's take this and let's pull this in, and optimal control doesn't take that much to be able to be there. So you can then say, if we allow this to be the interface, the interface problem is solved, right? There's actually not much more to be working on than that. That the interface took about 2 to 3 weeks to piece together based off the other things that ModelingToolkit had, right? Now, the pieces underneath that are like, okay, well, ModelingToolkit has to generate code and the solver has to take this code. Is this code as optimal as what I can get through, writing this Julia code by hand? And, if I want to hit parallelism, in GPUs, is it easier for me if I got this piece from CUDA, right? All those pieces still need to be worked out. And I think that the way that we can do this is we can, each solver that is trying to do something new and novel might need more information. And I think that what they just need to do is they need to demand, hey, ModelingToolkit has one way to define this ODE, but here is this connector step, right, where we define the problem. And my solver, my approach needs this extra information that no one's had before, right? Maybe it needs to be able to use DCP to be able to prove convexity or something complex. But at that step, we can just say, give me that extra information. I demand that from you. And if we listen to our developer ecosystem and we say, tell us what your demands are, and we'll make sure to keep on improving ModelingToolkit's code gen and its analysis systems to give you all the information you need, then everyone should be able to build their optimized versions of solvers on that. And then I think that we'll be in a pretty good spot. And that's where we've been kind of ending up so far, right? This is how we already have 4 backends, and then more and more kind of oncoming based off of this approach.
Thank you. Another question?
Just very briefly, because I was wondering in your earlier talk, because I don't know much about the ecosystem, I'm sort of new to this, but that I was wondering, okay, is this mainly geared towards commercial users? But now, also having seen this, I guess it's both academic and commercial users, but the idea is to also get those people who have specific domain knowledge in their field, but not necessarily all the technical knowledge in order to use this on a more fundamental level. Would you say that's fair?
Yeah, I mean, yeah. So I mean, I mentioned some of the commercial use cases just because, I mean, I had a sponsor talk earlier, and then, it's one of these cases where you end up with these gigantic systems of equations, right? So it's nice and cool to show those. But there's so many other things that people are doing with ModelingToolkit, right? So for example, someone posted today an entire version of cosmology models, right? Entire lambda CDM, right? The early universe equations all generated through ModelingToolkit. And so if you want to find out what would be the optimal universe, right? You could literally just do that now with the optimal control interface, right? And so, I think that the key thing here, right? The key piece is that building tools to solve problems on computable functions has limitations. But if you have symbolic information about it, then you can know what the mathematic is, and you can simplify things. You do all sorts of operations on that code. And when people say, hey, I'm building a domain-specific solver and I can do better than the general numerical code, it's the reason why they can do better than the general numeric code is because they've done some simplification. So what we could do is we could just say, hey, can I make those simplification tools all be a general thing called symbolics.jl? And can I make a modeling tool that is called ModelingToolkit, which can automatically do all those simplifications? And if I do that, do we need domain-specific tools anymore? Or can you just have one tool that is in targeting all the solvers, because all of that domain-specific pieces is just mathematical simplifications that are actually being reused across different domains. And this is what we're really aiming at, right? It's not about industrial or other pieces, right? It's biologists and ecologists do the same thing as physicists, right? You simplify your equations before you solve them. A computer program can't do that, but a high-level system can, and then maybe we can make a higher-level system that targets every solver.